46 billion light years away, there stands an invisible wall that marks the edge of everything we can ever see or know. Beyond this cosmic horizon lies a realm so mysterious that even our most advanced theories can only guess at what lurks there. We will journey past dying stars that rain liquid metal, through voids so vast they could swallow a million galaxies, and into dimensions where space itself might be an illusion. If you are ready to explore what lies beyond the edge of reality, hit that like button and subscribe, because we are about to venture where no human eye has ever looked. Prepare yourselves. We begin. Picture standing at the edge of a cliff, but instead of rocks below, there is nothing but endless mystery. This is where we find ourselves when we reach the boundary of the observable universe, a sphere stretching 93 billion light years across, with Earth sitting right at the center. You might think this edge is where space ends, but you would be wrong. This invisible wall exists not because space stops, but because light itself has limits. When you look at distant galaxies through the most powerful telescopes, you are actually looking backward through time. The light from these cosmic neighbors took millions or billions of years to reach your eyes. The farther you peer into space, the deeper you travel into the past. Eventually, you reach a point where the light has been traveling for so long that it carries images from when the universe was just 380,000 years old, a cosmic baby compared to its current age of nearly 14 billion years. This ancient light creates our cosmic horizon. Beyond this boundary, space continues to exist, filled with galaxies, stars, and planets we will never see. These hidden realms stretch outward in every direction, containing wonders that dwarf anything we have discovered in our local cosmic neighborhood. Imagine entire galactic clusters the size of our local group, spinning through the darkness just beyond our sight. Scientists estimate that for every galaxy we can observe, there are at least 23 more hiding beyond the edge. These invisible galaxies follow the same physical laws as ours, hosting planets where alien sunrises paint foreign skies in colors we cannot imagine. Some of these worlds orbit stars so massive, they would make our sun look like a grain of sand next to a basketball. The strangest part about this cosmic boundary is that it moves. Every second, light from slightly more distant regions reaches Earth for the first time, pushing our observable horizon outward at the speed of light. We are constantly discovering new territory, like explorers whose map expands as they walk. Yet this expansion happens so slowly that in a human lifetime, the edge moves only about 6 trillion miles farther out, a distance that sounds enormous, but represents just a tiny fraction of a light year. What makes this boundary even more mysterious is that different observers throughout the universe each have their own unique horizon. An alien astronomer living in a galaxy near our current edge would see completely different cosmic territories than we do. Their observable universe would overlap with ours in some regions, while revealing entirely new cosmic landscapes in others. Think of it like standing in a vast foggy field, where you can only see a certain distance in any direction. Move to a different spot, and your circle of visibility shifts, revealing new areas while hiding others. The universe works the same way, with each location serving as the center of its own observable sphere. But this wall of light is just the beginning of our journey into the unknown, because what lies beyond makes our visible universe look like a single raindrop in an infinite ocean. The oldest light in the universe whispers secrets about what lies beyond our cosmic horizon, and it comes from everywhere at once. This ancient glow, called the cosmic microwave background radiation, fills every cubic inch of space around us. When you tune an old television to static, about 1% of those dancing dots comes from this primordial light, photons that have been traveling through space since before the first stars were born. This radiation marks the moment when the universe became transparent for the first time. Before this cosmic dawn, space was so hot and dense that light could not travel more than a few inches without being absorbed or scattered. The entire universe glowed like the surface of the sun, but this light was trapped in an endless maze of bouncing particles. Then, as the expanding cosmos cooled, electrons and protons finally joined together to form the first atoms. Suddenly, light could travel freely across vast distances. The universe went from being opaque to crystal clear in what astronomers call the moment of last scattering. This transition happened everywhere simultaneously, creating a sphere of glowing gas that surrounded every point in space. The light from this cosmic flashbulb has been racing outward ever since, and we see it today as a faint microwave glow that bathes the entire sky. This background radiation carries a map of the early universe written in tiny temperature variations. Some regions were slightly hotter than others, and these differences show us where matter was beginning to clump together. These hot and cold spots would eventually grow into the cosmic web of galaxies and galaxy clusters we see today. The pattern reveals not just our past, but hints at the massive structures that exist beyond our observable boundary. The temperature differences are incredibly small. We are talking about variations of just a few millionths of a degree. Yet these tiny fluctuations represent density variations that stretched across regions millions of light years wide. When we map these patterns, we can trace them beyond our visible horizon and predict what kinds of structures should exist in the hidden universe. Scientists have discovered that the microwave background shows evidence of features larger than our entire observable universe. These cosmic superstructures appear as subtle patterns that suggest our visible cosmos is just one small section of a much grander architecture. It is like finding the edge of a massive city by studying the pattern of streetlights visible from your neighborhood. The radiation also carries clues about the shape of space itself. By measuring how the hot and cold spots are distributed across the sky, astronomers can determine whether the universe is curved like a sphere, saddle-shaped like a mountain pass, or flat, like an infinite sheet of paper. The answer has profound implications for what lies beyond our cosmic boundary. Current measurements suggest space is remarkably flat, which means it probably extends infinitely in all directions. This flatness implies that the regions beyond our horizon contain the same kinds of galaxies, stars, and planets we see in our local cosmic neighborhood, stretching onward without end. But this ancient afterglow is about to reveal something even more mind-bending about the true scale of reality. Deep within the cosmic microwave background lies a hidden sphere that represents the farthest we can ever see into the past. This sphere of last scattering surrounds us like a cosmic snow globe, marking the exact moment when the universe first became transparent. Beyond this ancient boundary, the laws of physics themselves conspire to hide the deeper mysteries of space and time. The sphere sits at a distance of 45 billion light-years from Earth, even though the light took only 380,000 years to reach us. This mind-bending contradiction happens because space itself has been expanding while the photons traveled toward us. Picture an ant walking across a balloon that someone is steadily inflating. The ant moves forward, but the balloon's surface stretches beneath its feet, making the final distance much greater than the path it walked. When we peer at this sphere, we are witnessing the universe at just 1/700th of its current age. Back then, the entire cosmos was only about 3,000 degrees Fahrenheit, hot enough to melt copper, but cool enough for the first atoms to form. The universe had shrunk from the size of a grapefruit to roughly 1,000th of its current scale, yet it still stretched farther than we can imagine. This ancient sphere reveals patterns that extend far beyond what we can see today. The hot and cold spots in the microwave background show correlations across distances larger than our current observable universe. These patterns are like seeing parts of a vast painting that extends beyond the edges of your window frame. You can tell there is more artwork outside your view, following the same artistic style and color scheme. Scientists have identified features in the sphere that span angles larger than 2 degrees across the sky. This might sound small, but remember that we are looking at the most distant observable surface in the universe. An angle of 2 degrees at this cosmic distance represents a physical size of about 1 billion light-years. The fact that these enormous regions show coordinated patterns suggests they were once close enough together to influence each other. The sphere also shows us that the universe was incredibly smooth in its youth. The temperature variations across this ancient surface differ by only about 1 part in 100,000. This smoothness creates a puzzle, because regions on opposite sides of the sphere could never have communicated with each other through light signals. Yet somehow, they managed to reach almost exactly the same temperature. This puzzle points towards something extraordinary that happened before the sphere of last scattering formed. The universe must have undergone a period of incredibly rapid expansion that stretched small, connected regions to enormous sizes. During this cosmic inflation, areas that were once neighbors became separated by distances larger than light could travel. The patterns frozen into the sphere of last scattering represent quantum fluctuations that were stretched to cosmic proportions during this inflationary epoch. These tiny variations in the quantum foam became the seeds that would eventually grow into galaxies, galaxy clusters, and the cosmic web. In essence, we are seeing the quantum mechanical birth cries of cosmic structure itself. But this sphere represents just the beginning of our journey backward through time, because the universe underwent even more dramatic transformations in the moments before it became transparent. In the invisible realms beyond our cosmic horizon, vast kingdoms of dark matter weave through space like ghost empires. These shadowy domains contain 5 times more mass than all the stars and galaxies we can see, yet they remain completely invisible to our most powerful telescopes. What we observe in our local universe represents just the glowing tips of cosmic icebergs, while the real bulk of matter lurks hidden in the darkness. Dark matter particles stream through your body right now at speeds of hundreds of miles per second. Millions of these invisible bullets pass through every square inch of your skin each second, yet you feel nothing because they barely interact with ordinary matter. They are like cosmic ghosts, present everywhere but touching nothing. This ethereal substance shapes the architecture of the universe while remaining forever beyond our direct perception. The hidden universe contains dark matter structures that dwarf anything made of ordinary matter. Imagine cosmic scaffolding built from invisible threads, with galaxy clusters hanging like holiday ornaments from a framework we cannot see. These dark matter halos extend far beyond the visible edges of galaxies, creating spheres of invisible mass that can stretch for millions of light years. Computer simulations reveal that dark matter forms intricate cosmic webs throughout the universe. These simulations show vast filaments of dark matter connecting distant galaxy clusters with enormous voids stretching between them. The largest dark matter structures span hundreds of millions of light years, creating a cosmic architecture that exists primarily in the hidden universe beyond our observable boundary. Some of these dark matter kingdoms exist in total isolation, containing no ordinary matter at all. These ghost galaxies would be completely invisible to us, even if they were sitting right next to the Milky Way. They represent pure gravitational sculptures, shaped by forces we can detect only through their effects on nearby visible matter. Entire cosmic empires could exist in these dark realms, governed by physics we are only beginning to understand. The dark matter in our observable universe shows patterns that extend far beyond what we can see. Galaxy surveys reveal that dark matter halos are aligned across distances of hundreds of millions of light years, suggesting that the invisible scaffolding follows organized patterns throughout the broader cosmos. These alignments point toward dark matter superstructures that stretch across our cosmic horizon into the hidden universe. Scientists have discovered that dark matter moves differently than ordinary matter in the early universe. While normal matter got caught up in the cosmic plasma and could not form structures until after the sphere of last scattering, dark matter was already building cosmic architecture during the universe's first few 100,000 years. This head start means that the dark matter universe developed a more complex structure than the visible cosmos we see today. The gravitational effects of dark matter also influence the cosmic microwave background, leaving subtle fingerprints that reveal information about the hidden universe. These patterns show that dark matter was already forming massive structures when the universe was just a few 100,000 years old, creating gravitational wells that would eventually become the largest galaxy clusters. Beyond our cosmic horizon, dark matter continues this architectural project on scales we can barely comprehend. The hidden universe contains dark matter structures so massive that our entire observable cosmos might fit comfortably inside just one of their gravitational halos. But dark matter represents just one component of the invisible universe, because an even more mysterious force is actively reshaping cosmic architecture on the grandest scales imaginable. Before the cosmic microwave background formed, the universe underwent the most violent expansion in cosmic history. During the first tiny fraction of a second after the Big Bang, space itself stretched faster than the speed of light, growing from smaller than a proton to larger than a grapefruit in less time than it takes light to cross an atomic nucleus. This inflationary epoch explains why regions beyond our cosmic horizon exist at all. Imagine a deflated balloon with two ants sitting right next to each other on its surface. Now picture that balloon inflating so rapidly that within 1 second the ants find themselves separated by a distance larger than the entire observable universe. This is essentially what happened to space during cosmic inflation, except the expansion was far more extreme and happened much faster. The inflationary period solved several cosmic mysteries that had puzzled scientists for decades. Before inflation, astronomers could not explain why the universe looks almost exactly the same in every direction. Regions of space that should never have been able to communicate with each other somehow reached identical temperatures and densities. Inflation explains this by proposing that all the regions we can see today were once squeezed together in a volume smaller than an atom. During inflation, quantum fluctuations in the fabric of space itself got stretched to cosmic proportions. These tiny ripples in the quantum foam became the seeds for all the galaxies and galaxy clusters we see today. The hot and cold spots in the cosmic microwave background represent these quantum fluctuations, preserved like fossilized waves from the universe's most violent moment. The energy driving inflation came from a special kind of field that created negative pressure in space. Unlike ordinary matter, which slows down cosmic expansion through gravity, this inflation field caused space to expand faster and faster. The more it expanded, the more energy it contained, creating a runaway process that doubled the size of the universe every tiny fraction of a second. Scientists estimate that during its brief reign, inflation increased the size of the universe by a factor of at least 10 to the 26th power. To put this in perspective, if a grain of sand expanded by this same factor, it would become larger than our entire observable universe today. This incredible stretching explains why space appears so flat and uniform across vast distances. The end of inflation was as dramatic as its beginning. When the inflation field finally decayed, it released all its stored energy in a process called reheating. This energy became the hot plasma that eventually cooled to form the cosmic microwave background. The transition from inflation to the hot Big Bang happened in less than a trillionth of a trillionth of a trillionth of a second. Inflation theory predicts that our observable universe represents just one tiny patch of a much larger inflated space. Beyond our cosmic horizon, inflation created regions that underwent slightly different expansion histories. Some areas might have inflated for longer periods, creating spaces with different physical properties or even different numbers of dimensions. The quantum fluctuations stretched during inflation were not perfectly uniform. Some regions received slightly more expansion than others, creating variations that persist today as differences in cosmic density. These variations suggest that the hidden universe contains regions where matter is more or less concentrated than in our local cosmic neighborhood. But inflation itself may not have stopped everywhere at once, which leads us to one of the most mind-bending possibilities in modern cosmology. Beyond our cosmic horizon, inflation may still be happening, creating new universes faster than we can count. While our region of space settled into a stable expansion billions of years ago, the inflation field might continue to stretch and spawn baby universes throughout an eternal cosmic landscape. This ongoing process would create not just more space, but entirely separate pocket universes with their own physical laws and constants. Picture a pot of boiling water where bubbles constantly form and rise to the surface. In this cosmic analogy, our entire observable universe is just one tiny bubble in an infinite ocean of space-time that continues to boil and create new bubbles without end. Each bubble represents a separate universe with its own Big Bang, its own evolution, and potentially its own versions of physics. The multiverse hypothesis suggests that inflation never truly ends on a global scale. While specific regions like ours transition from inflation to normal expansion, the broader inflating space continues to grow exponentially. This eternal inflation creates a fractal structure where universes spawn other universes in an endless hierarchy of cosmic reproduction. Some of these pocket universes might have formed with different values for fundamental constants like the strength of gravity or the mass of electrons. In universes where gravity is slightly stronger, stars would burn out faster and black holes would dominate cosmic evolution. In universes where gravity is weaker, matter might never clump together enough to form galaxies at all. The multiverse could contain every possible combination of physical laws. The distance scales involved in the multiverse are so vast, they make our observable universe seem like a speck of dust. Even if we could travel at the speed of light, we would never reach another pocket universe because the space between them expands faster than we could cross it. These cosmic neighbors remain forever beyond our reach, separated by barriers of exponentially growing space-time. Within this multiverse, our universe represents just one possible outcome of cosmic evolution. There might be pocket universes where Earth never formed, where life evolved completely differently, or where the laws of physics themselves follow alternative mathematical structures. The multiverse contains not just more space, but more possibilities than we can imagine. Some versions of multiverse theory suggest that quantum mechanics creates new universes every time a quantum measurement occurs. In this many worlds interpretation, reality constantly branches into parallel timelines. Every quantum coin flip creates universes where the coin lands both heads and tails, leading to an infinite proliferation of parallel realities. The mathematics of eternal inflation shows that even the most unlikely events must happen somewhere in the multiverse, given infinite space and time. There could be pocket universes where history unfolded exactly like ours, except for tiny differences, creating cosmic twins of Earth where alternate versions of humanity evolved under slightly different circumstances. Scientists have proposed several ways the multiverse might leave detectable signatures in our cosmic microwave background. Collisions between pocket universes could create circular patterns in the ancient light, while gravitational effects from neighboring universes might produce subtle distortions in space-time that we could measure with future technology. The multiverse challenges our understanding of what makes our universe special, suggesting instead that we inhabit just one random pocket in an infinite cosmic lottery. Across the vast expanse of the multiverse, cosmic catastrophes unfold as entire universes crash into each other like soap bubbles in infinite space. These collisions between pocket universes create the most violent events imaginable, releasing energies that dwarf anything we have witnessed in our local cosmic neighborhood. The aftermath of these cosmic crashes might even be detectable in our own sky. When two expanding universe bubbles meet, their boundaries merge in a process that fundamentally alters the fabric of space and time within both regions. The collision zone becomes a cosmic battlefield where different physical laws clash and compete for dominance. Imagine two different sets of physics meeting head-on, with the laws of nature themselves becoming unstable and chaotic. The energy released during a bubble collision exceeds anything our universe has experienced since its own Big Bang. These cosmic crashes generate gravitational waves so powerful they would ripple through the multiverse for billions of years. The collision zones become cosmic scars, where space itself bears permanent marks from the violence of universal warfare. Scientists have calculated that these bubble collisions would leave distinctive circular patterns in the cosmic microwave background radiation. These collision signatures would appear as rings of slightly hotter or cooler temperature variations, marking places where shock waves from cosmic crashes reached our universe during its formation. Several research teams have claimed to detect such patterns, though the evidence remains controversial. The timing of bubble collisions depends on the complex dynamics of eternal inflation. Some pocket universes might collide while they are still young and hot, creating spectacular fireworks as their Big Bang energies merge. Other collisions happen between mature universes with established galaxies and stars, leading to cosmic apocalypses that destroy entire civilizations across multiple realities. During a collision, the boundary between two universes becomes a zone of exotic physics where the normal rules break down completely. Space might develop extra dimensions, time could flow in multiple directions simultaneously, and matter might transform into forms of energy that do not exist in either parent universe. These boundary regions represent laboratories of impossible physics. The geometry of bubble collisions creates fascinating patterns in the multiverse. When three or more universe bubbles meet at a single point, they form cosmic vertices where multiple realities intersect. These intersection zones might harbor forms of existence that transcend the limitations of any single universe, creating cosmic crossroads where travelers could theoretically move between different realities. Some collision scenarios result in the complete merger of two pocket universes, creating larger cosmic bubbles with hybrid physical laws. These merged universes might inherit properties from both parents, leading to cosmic environments with capabilities that exceed either original universe. The resulting hybrid realities could support forms of life and consciousness that require multiple sets of physical laws to exist. The frequency of bubble collisions depends on the overall structure of the multiverse. If pocket universes form close together in cosmic terms, collisions would be common and violent. If they emerge from inflation more spread out, collisions would be rare cosmic events that mark special moments in multiverse history. Our own universe might bear subtle scars from ancient collisions that occurred during its formation, hidden within the patterns of galaxies and cosmic structure we see today. Step back and imagine the most overwhelming possibility of all, that space simply goes on forever in every direction, with no edge, no boundary, and no end. This infinite cosmos would contain everything that could possibly exist, repeated endlessly across vast distances that dwarf our observable universe. In such a reality, every possible arrangement of matter and energy must occur somewhere in the limitless expanse of space. An infinite universe creates paradoxes that challenge our understanding of uniqueness and identity. If space truly extends forever, then the exact arrangement of atoms that makes up Earth, our solar system, and even your own body must be repeated countless times across cosmic distances. There would be perfect copies of you living identical lives on planets scattered throughout the infinite void. The mathematics of infinity shows that in limitless space, even the most improbable events become inevitable. Somewhere in the cosmic distance, there exists a planet where dinosaurs never went extinct and evolved into intelligent beings who built technological civilizations. In another region, the laws of physics might allow magic to work, creating worlds where the impossible becomes routine. This infinite repetition occurs because there are only a finite number of ways to arrange matter within any given volume of space. Once you have exhausted all possible configurations within a sphere the size of our observable universe, the patterns must begin repeating. The distance between identical copies depends on the number of possible arrangements, which scientists estimate creates exact duplicates roughly every 10 to the 10 to the 120 meters. These cosmic distances are so vast, they make our observable universe seem like a grain of sand on an infinite beach. The nearest perfect copy of Earth lies farther away than a number, with more digits than there are atoms in our entire visible cosmos. Yet, in an infinite universe, this unimaginably distant duplicate would be as real and valid as the planet beneath your feet right now. The infinite universe hypothesis suggests that our cosmic horizon acts like a moving window through an endless landscape. As the universe ages and our observable boundary expands, we continuously discover new territories that were always there, waiting to be revealed. Each moment brings previously hidden galaxies into view for the first time. Within infinite space, every possible form of cosmic evolution must play out somewhere. There are regions where galaxies formed earlier and evolved differently, creating cosmic neighborhoods filled with ancient civilizations that solved the mysteries of existence billions of years ago. Other areas might contain universes where stars never formed, leaving infinite dark spaces populated only by lonely planets wandering through the void. The concept of infinite space also means that there are no preferred locations or special positions in the cosmos. Our galaxy sits at the center of our observable universe only because that is where we happen to be located. Every other point in infinite space serves as the center of its own observable sphere, each revealing different territories of the endless cosmic landscape. An infinite universe would contain not just more matter and energy, but more possibilities than we can comprehend. Every story that could be told, every scientific discovery that could be made, and every work of art that could be created already exists somewhere in the limitless expanse. But even infinity might not be the strangest possibility for what lies beyond our cosmic boundary. Beyond our observable horizon, the largest structures in the universe form a cosmic web so vast and intricate that our entire visible cosmos represents just one tiny knot in an infinite tapestry. This hidden architecture consists of dark matter filaments stretching across hundreds of millions of light years, connecting galaxy clusters like cosmic highways through the void. The patterns we see in our local neighborhood are just small fragments of a grand design that extends far beyond what any telescope can reveal. The cosmic web emerged from tiny quantum fluctuations that were stretched to enormous scales during cosmic inflation. These primordial seeds grew under the influence of gravity for billions of years, creating a foam-like structure where matter collects along intersecting filaments, while vast empty regions called cosmic voids separate them. The result resembles a three-dimensional spiderweb made of galaxies and dark matter. Computer simulations reveal that the cosmic web follows mathematical patterns that repeat across different scales. The same branching structures that connect galaxy clusters also appear when zooming in on smaller regions, creating a fractal architecture that extends from the largest cosmic scales down to individual galaxy groups. This self-similar design suggests that the hidden universe beyond our horizon continues the same intricate patterns we observe locally. The filaments of the cosmic web contain most of the matter in the universe, yet they remain largely invisible to our instruments. These cosmic highways consist primarily of dark matter and hot plasma that glows too faintly for current telescopes to detect. Future space missions may reveal this hidden architecture by mapping the faint glow of plasma heated as it flows along the filamentary structures. Where cosmic filaments intersect, they create massive galaxy clusters that serve as cosmic cities in the web. These intersection points concentrate matter and energy on scales that dwarf individual galaxies. The largest galaxy clusters contain thousands of galaxies bound together by gravity wells, so deep they bend space and time into cosmic lenses that magnify distant objects. Between the filaments lie cosmic voids so empty they challenge our understanding of space itself. These regions contain less than one galaxy per volume that would normally hold dozens, creating cosmic deserts where space stretches for hundreds of millions of light years with almost nothing to mark the distance. Some voids are so large that light takes longer to cross them than the current age of the universe. The cosmic web continues to evolve as dark energy accelerates the expansion of space. Over billions of years, the accelerating expansion will stretch the filaments until they snap, leaving galaxy clusters isolated as cosmic islands in an ever-expanding sea of empty space. Eventually, the web will dissolve completely, marking the end of large-scale cosmic structure. Scientists have discovered that galaxies align along the cosmic web filaments in ways that affect their star formation and evolution. Galaxies in dense filaments tend to be older and contain less gas for making new stars, while galaxies in voids often appear younger and more actively star-forming. These environmental effects influence cosmic evolution across the entire web. The hidden architecture of the cosmic web also affects the motion of galaxies through space. The Great Attractor, a massive gravitational anomaly that pulls our local group of galaxies through space at 600 miles per second, may be connected to large-scale structures in the cosmic web that extend far beyond our observable boundary. But the cosmic web itself may be embedded within even larger structures that challenge our understanding of space and dimensionality. In the deepest reaches of space, beyond our cosmic horizon, lie regions so empty they defy comprehension, supervoids that span billions of light years and contain almost nothing but darkness and distance. These cosmic deserts are so vast that our entire observable universe could fit comfortably inside just one of them, like a marble rattling around inside a football stadium. Within these voids, space itself seems to stretch endlessly without galaxies, stars, or any visible landmarks to break the monotony. The largest known supervoid in our observable universe, called the cold spot, spans 1.8 billion light-years across and contains roughly 10,000 times less matter than average regions of space. This cosmic desert is so empty that a traveler crossing it at the speed of light would journey for nearly 2 billion years through almost complete darkness, passing perhaps only a few dozen galaxies along the way. These supervoids formed when matter flowed out of low-density regions during cosmic evolution, leaving behind areas where gravity could not collect enough material to form normal cosmic structures. The expansion of space gradually stretched these empty regions until they became cosmic canyons, separating the densest parts of the cosmic web. Over billions of years, they grew into the largest structures in the universe. Within supervoids, the few galaxies that do exist follow different evolutionary paths than their counterparts in denser regions. These cosmic hermits often appear younger and bluer than typical galaxies, suggesting they formed stars more recently or maintained higher rates of star formation. The isolation and low-density environment of supervoids may provide ideal conditions for galaxy formation and evolution that differs dramatically from the cosmic norm. The boundaries of supervoids create cosmic shock fronts where empty space meets the filaments of the cosmic web. These transition zones span tens of millions of light-years and represent some of the most dynamic regions in the universe. Matter flows along these boundaries like cosmic rivers, feeding galaxy formation in the denser regions while leaving the void interiors increasingly empty. Scientists have discovered that supervoids affect the cosmic microwave background radiation in measurable ways. Photons traveling through these regions experience less gravitational redshift than normal, creating cold spots in the ancient light that mark the locations of cosmic voids. These signatures allow astronomers to map void structures that existed when the universe was much younger. The existence of supervoids beyond our cosmic horizon would create regions where space expansion behaves differently than in our local neighborhood. In the emptiest voids, dark energy dominates cosmic dynamics more completely than anywhere else, potentially creating pockets where space expands faster than the cosmic average. These regions might serve as preview of the universe's ultimate fate. Some supervoids may be so large and empty that they create cosmic islands completely isolated from the rest of the universe. Galaxies trapped within the deepest voids might lose contact with the broader cosmic web as space expansion carries them beyond the reach of light signals. These cosmic castaways would evolve in complete isolation, unaware that a larger universe exists beyond their empty domain. The temperature of space itself differs within supervoids, creating cosmic climate zones where the background radiation is colder than average. These temperature variations affect the physics of any matter present, potentially altering how stars form and evolve within void galaxies. The cosmic microwave background becomes a cosmic thermometer that reveals these hidden climate differences. Future surveys may discover supervoids so large they challenge our understanding of cosmic structure formation, revealing empty regions that approach the size of our entire observable universe and contain mysteries that transform our vision of cosmic architecture. Beyond our cosmic horizon, a mysterious force stronger than gravity itself is tearing the fabric of space apart at ever-increasing speeds. This dark energy makes up 70% of everything that exists, yet we have no idea what it actually is or where it comes from. What we do know is terrifying. This invisible force is winning a cosmic war against gravity, and its victory will determine the ultimate fate of every galaxy, star, and atom in existence. Dark energy behaves like anti-gravity on cosmic scales, pushing space apart instead of pulling matter together. Unlike normal matter and energy that become diluted as the universe expands, dark energy maintains constant density even as space stretches. This means that as the universe grows larger, the total amount of dark energy increases, making its repulsive effects stronger over time. The discovery of dark energy came as a shock to astronomers studying distant supernovas in the late 1990s. These cosmic explosions were dimmer than expected, indicating they were farther away than predicted by models of cosmic expansion. Instead of slowing down due to gravity, the universe was actually accelerating its expansion rate. This revelation overturned decades of cosmological theory in a single observation. In regions beyond our observable boundary, dark energy operates without any opposition from matter or radiation. These cosmic frontiers represent laboratories where we can understand dark energy in its purest form uncontaminated by the gravitational effects of galaxies and galaxy clusters. Here, space expands at rates that would tear apart any normal matter in seconds. The accelerating expansion, driven by dark energy, creates cosmic event horizons, similar to those around black holes. Galaxies currently visible at the edge of our cosmic boundary will eventually disappear forever as space carries them beyond the reach of light signals. Once these cosmic neighbors cross this dark energy horizon, no information from them can ever reach us again. Scientists have proposed dozens of theories to explain dark energy, from modifications to Einstein's theory of gravity to exotic quantum fields that permeate space. Some models suggest dark energy represents the energy of empty space itself, while others propose it arises from extra dimensions of space that we cannot directly perceive. The true explanation remains one of the greatest mysteries in science. The strength of dark energy appears remarkably fine-tuned for the existence of cosmic structure. If dark energy were slightly stronger, it would have prevented galaxies from forming by tearing apart matter clumps before gravity could bind them together. If it were weaker, the universe might have collapsed back on itself before stars could evolve and create the heavy elements necessary for life. Future observations may reveal whether dark energy remains constant or changes over cosmic time. Some theoretical models predict that dark energy could suddenly increase in strength, leading to a Big Rip scenario, where accelerating expansion becomes so violent it tears apart molecules, atoms, and even atomic nuclei. Other models suggest dark energy might decay, potentially triggering new phases of cosmic evolution. The regions beyond our horizon may already be experiencing these exotic phases of dark energy evolution, creating cosmic laboratories where the future of our own universe is being written in real time. At the smallest scales of space and time, reality itself becomes a bubbling foam of quantum uncertainty that challenges everything we think we know about the nature of existence. Beyond our cosmic horizon, this quantum foam might behave in ways that transform the very meaning of space, time, and matter. At distances smaller than the Planck length, a scale so tiny that a proton appears larger than our solar system, the smooth fabric of spacetime dissolves into a chaotic dance of virtual particles and fluctuating geometry. The quantum foam emerges from the fundamental uncertainty principle that governs all quantum mechanics. Even in completely empty space, energy and matter constantly pop into existence as particle pairs before annihilating each other in time intervals, so brief they occur faster than any measurement could detect them. These virtual particles borrow energy from the quantum vacuum and must pay it back before the universe notices the debt. During cosmic inflation, quantum fluctuations in this foam were stretched from subatomic scales to cosmic proportions, becoming the seeds for all galaxies and large-scale structures we observe today. The hot and cold spots in the cosmic microwave background represent fossilized quantum foam, preserved like ancient bubbles in cosmic amber. What we see as the majestic architecture of the universe began as random quantum noise. At the Planck scale, space and time themselves become uncertain and fluctuating. The normal concepts of distance and duration break down completely, replaced by a probabilistic quantum geometry where cause and effect lose their usual meanings. In these regions, time might flow in multiple directions simultaneously, while space could branch and merge like the tributaries of a cosmic river. Some theories suggest that the quantum foam contains microscopic black holes that constantly form and evaporate through Hawking radiation. These quantum black holes would be smaller than atomic nuclei, but contain the massive mountains, creating intense gravitational fields that warp spacetime on the smallest possible scales. The foam becomes a cosmic battlefield where gravity and quantum mechanics clash in ways we cannot yet understand. The quantum foam might also harbor virtual particles with properties that do not exist in our normal universe. These exotic quantum entities could carry charges or energies that violate the known laws of physics, existing only in the brief moments before they vanish back into the vacuum. The hidden universe beyond our horizon might be filled with regions where these exotic particles become real and stable. Scientists have proposed that consciousness itself might emerge from quantum processes in the foam, suggesting that the universe possesses a form of awareness at its most fundamental level. If true, The regions beyond our cosmic boundary might contain forms of quantum consciousness that operate on scales and timescales completely alien to biological life. The geometry of quantum foam follows mathematical patterns that repeat across all scales of existence. The same fractal structures that appear in quantum fluctuations also manifest in galaxy distributions and cosmic web architecture. This suggests that the universe preserves the memory of its quantum origins, even as it grows to cosmic proportions. Future theories of quantum gravity may reveal that the quantum foam represents the fundamental pixels of reality, with space and time emerging as collective properties of countless quantum bits of information. In this view, the universe beyond our horizon might consist of pure quantum information, with matter and energy arising as higher-level patterns in an underlying computational substrate. But the quantum foam itself might be embedded within dimensions of space that extend far beyond the three we experience in everyday life. The space we experience every day, with its familiar length, width, and height, might represent just a tiny slice of a much larger reality containing 6, 7, or even 11 dimensions that extend beyond our cosmic horizon. These hidden dimensions could be curled up so tightly that we cannot detect them directly, or they might stretch infinitely through realms where the normal rules of physics transform into something completely alien to our three-dimensional experience. Imagine living your entire life on the surface of a sheet of paper, able to move only forward, backward, left, or right. To you, the universe would appear two-dimensional, and the concept of up or down would be incomprehensible. Now imagine that our three-dimensional reality might be like that sheet of paper, embedded within a higher dimensional space that we cannot perceive or explore with our limited senses. String theory, one of the leading candidates for a unified theory of physics, requires the existence of these extra dimensions to make its mathematics work correctly. According to string theory, the fundamental particles we observe are actually tiny vibrating strings that extend into these hidden dimensions. The different ways the strings vibrate in higher dimensional space determine whether they appear as electrons, quarks, photons, or other particles in our three-dimensional slice of reality. These extra dimensions might be compacted into shapes so small they exist at the Planck scale, billions of times smaller than an atomic nucleus. At every point in our three-dimensional space, there could be an entire hidden universe of 6 additional dimensions, curled up like microscopic origami that contains its own complex geometry and physics. The total volume of these hidden dimensions at every point might be larger than our entire observable universe. Alternatively, some dimensions might extend infinitely through space parallel to our own, creating a cosmic bulk where our universe represents just one three-dimensional membrane floating in a higher dimensional ocean. Other membrane universes could exist nearby in the extra dimensions, completely invisible to us because light and matter cannot travel through the higher dimensional bulk that separates us. The laws of physics might operate very differently in higher dimensional space. Gravity, which appears weak in our three-dimensional world, could become much stronger when it spreads through additional dimensions. This could explain why gravity is so much weaker than the electromagnetic and nuclear forces. Most of its strength might be diluted by leaking into dimensions we cannot access. Particles and energy might be able to take shortcuts through higher dimensional space, traveling distances that would be impossible in our three-dimensional reality. What appears as empty space to us might be filled with matter and energy moving through parallel dimensions, creating gravitational effects we can detect but cannot directly observe. The regions beyond our cosmic horizon might contain areas where the extra dimensions unfold and become macroscopic, creating zones where space suddenly expands from 3 dimensions to 4, 5, or more. In these regions, matter could move in directions that do not exist in our reality, and physical laws might allow phenomena that would be impossible in three-dimensional space. Some theories propose that consciousness itself requires higher dimensional space to operate, suggesting that awareness represents a higher dimensional phenomenon that projects into our three-dimensional reality. If true, the hidden dimensions might be populated with forms of consciousness that exist on scales and in ways we cannot imagine. But higher dimensions represent just one way that the hidden universe might transcend the limitations of ordinary space and time. Beyond our cosmic horizon lies a vast landscape of possible realities where the fundamental laws of physics can take on millions of different forms. String theory predicts that the hidden dimensions of space can be configured in approximately 10 to the 500th different ways, creating a cosmic landscape where each configuration produces a universe with its own unique set of physical constants and particle properties. This string landscape makes our reality just one island in an ocean of alternative physics. Each point in the string landscape represents a different vacuum state where strings vibrate in characteristic patterns that determine the properties of matter and energy. In some regions of this landscape, electrons might be 1,000 times heavier than in our universe, making atoms so massive that chemistry as we know it could not exist. In other areas, the strong nuclear force might be weaker, preventing the formation of atomic nuclei and leaving only a universe of isolated protons and neutrons. The string landscape contains solutions where space has different numbers of dimensions in different regions. While our local area settled into 3 large spatial dimensions with 6 compactified extras, other parts of the landscape might support universes with 4, 5, or even 2 large dimensions. Life in these alternative geometries would follow completely different principles, with beings potentially evolving forms of existence that we cannot comprehend. Transitions between different regions of the string landscape could occur through quantum tunneling events that fundamentally alter the laws of physics across vast cosmic domains. These phase transitions would create expanding bubbles of new physics that spread at the speed of light, transforming everything they encounter. Our universe might be surrounded by regions where such transitions are actively occurring. The landscape includes configurations where the cosmological constant takes on different values, leading to universes that expand at different rates or even contract back toward big crunches. Some solutions produce universes that oscillate between expansion and contraction, creating cosmic cycles that repeat endlessly with slightly different physical laws in each iteration. Within the string landscape, there exist solutions that support multiple types of matter beyond the particles we know. These alternative physics regimes might contain dozens of different species of quarks and leptons, creating a rich zoo of particle interactions that could lead to forms of chemistry and biology based on entirely different principles than those that govern life on Earth. The mathematics of string theory suggests that most points in the landscape correspond to universes that are hostile to the formation of complex structures. The vast majority of possible string vacua produce realities where stars cannot form, atoms are unstable, or space itself is too chaotic to support persistent patterns. Our universe occupies a rare, special region where the laws of physics permit complexity in life. Some string theorists propose that eternal inflation continuously explores different regions of the landscape, creating pocket universes with randomly selected physical laws. This process would generate an infinite multiverse, where every possible configuration of string theory eventually manifests as a real universe somewhere in the cosmic bulk. The landscape might also contain solutions where time itself behaves differently, flowing at varying rates or even branching into multiple temporal dimensions. In these exotic regions, causality could operate according to principles that make our linear experience of past, present, and future seem like a primitive approximation of temporal reality. Navigation through the string landscape requires overcoming enormous energy barriers that separate different vacuum states, making transitions between different physics regimes extremely rare events that might occur only once per cosmic age. Floating through higher dimensional space like vast sheets in a cosmic wind, parallel universe membranes might exist just millimeters away from our reality, in dimensions we cannot perceive. These membrane universes, or brains as physicists call them, could harbor entire civilizations living out their histories in spaces that remain forever parallel to our own. What we experience as our complete reality might be just one thin slice of existence in a higher dimensional bulk populated by countless other membrane worlds. The concept of brain cosmology emerged from string theory's prediction that our universe could be confined to a 3-dimensional membrane floating in a space with up to 11 dimensions. Gravity can leak between these membranes through the higher dimensional bulk, but matter and light remain trapped on their respective branes, like insects stuck to parallel sheets of cosmic flypaper. These parallel membranes might be separated by distances smaller than the width of a human hair, yet the separation occurs in directions our three-dimensional senses cannot detect. An entire parallel Earth could exist less than an inch away from you right now, in a direction called Anna or Kata that extends perpendicular to all three spatial dimensions we can perceive. The parallel universes on nearby membranes might have evolved very differently than our own, even if they started with similar initial conditions. Small differences in the spacing between membranes or the properties of the higher dimensional bulk could lead to alternative histories where dinosaurs never went extinct, where different elements formed in stellar cores, or where the laws of physics evolved along completely different trajectories. Collisions between membrane universes could explain the Big Bang itself. When two branes crash together in the higher dimensional bulk, the enormous energy release could create the hot, dense conditions that we observe in our cosmic microwave background. Our universe might be the aftermath of such a collision, with the parallel membrane that struck us now moving away through dimensions we cannot follow. The gravitational effects of nearby membrane universes might be detectable through subtle influences on the motion of matter in our reality. Dark matter could represent the gravitational shadow cast by ordinary matter living on a parallel brane, creating invisible mass that we can detect only through its gravitational effects. The missing matter we attribute to dark matter might actually be perfectly ordinary matter living in a parallel universe. Some brane models predict that the parallel membranes oscillate toward and away from each other in the higher dimensional bulk, creating cycles where membrane universes alternately approach and separate over cosmic timescales. During close approaches, the gravitational interactions between branes could trigger episodes of accelerated expansion or contraction in both universes simultaneously. The temperature and density of the higher dimensional bulk between membranes might support forms of existence that transcend the limitations of membrane-bound matter. Bulk beings could potentially move freely between parallel universe membranes, appearing as mysterious phenomena that violate the normal laws of physics when they briefly interact with our three-dimensional reality. Communication between parallel membrane universes might be possible through gravitational signals that can propagate through the higher dimensional bulk. Advanced civilizations living on nearby branes might be sending gravitational wave messages that we could detect and decode with sufficiently sensitive instruments. The properties of space and time might differ slightly between parallel membranes, creating alternative realities where causality operates according to different rules, or where time flows at different rates. What seems like a single moment in our universe might correspond to entire eras in a nearby parallel reality. But the strangest effects of parallel membranes might emerge at the cosmic boundaries where space and time themselves begin to break down. At the edge of our observable universe, time itself begins to behave in ways that challenge our understanding of cause, effect, and the very nature of existence. The extreme gravitational fields and accelerating expansion near cosmic boundaries create time dilation effects so severe that a single second experienced by a distant observer might correspond to billions of years passing in our reference frame. These temporal distortions transform the cosmic edge into a realm where past, present, and future lose their familiar meanings. The expansion of space creates a cosmic horizon similar to the event horizon around a black hole. As galaxies approach this boundary, they appear to slow down and freeze from our perspective, their light becoming increasingly redshifted until it fades beyond detection. From their own viewpoint, however, these cosmic travelers continue their normal evolution, completely unaware that they appear frozen in time to distant observers. Near the cosmic boundary, the fabric of space-time becomes so curved by dark energy and gravitational effects that clocks run at dramatically different rates depending on their location and motion. An astronaut traveling toward the edge of our observable universe would experience time passing normally, but radio signals sent back to Earth would arrive with increasing delays, eventually taking billions of years to cross distances that once required only minutes. The cosmic microwave background radiation experiences extreme time dilation as it travels from the edge of the observable universe toward Earth. Photons that were emitted when the universe was only 380,000 years old have been traveling for nearly 14 billion years from our perspective, yet from the photon's viewpoint, the journey occurs instantaneously due to special relativistic effects. Regions beyond our cosmic horizon might exist in temporal states that correspond to different epochs of cosmic history. Areas that appear to be in our universe's future might actually represent alternative evolutionary paths where time flows according to different physical laws. The boundary between our observable universe and the hidden regions beyond might mark a transition between different temporal regimes. The gravitational time dilation near cosmic boundaries could create closed time-like curves where cause and effect become circular. In these regions, events might be able to influence their own past, creating temporal paradoxes that resolve themselves through quantum mechanical effects. The cosmic edge becomes a laboratory for studying the relationship between gravity, quantum mechanics, and the arrow of time. Some theoretical models predict that the cosmic boundary experiences time reversal effects, where entropy decreases and events unfold backward from our perspective. These time-reversed regions might contain matter that flows from the future toward the past, creating cosmic domains where causality operates in reverse. The boundary between normal time flow and time reversal could mark the edge of physical reality itself. The extreme time dilation near cosmic boundaries affects the evolution of any matter present in these regions. Stars near the cosmic edge might appear to burn for trillions of years from our perspective, even though they complete normal stellar life cycles in their own reference frames. Black holes in these regions could evaporate through Hawking radiation while appearing frozen in time to distant observers. Future space missions that attempt to approach the cosmic boundary would experience increasingly severe time dilation effects as they travel farther from Earth. The crews of such missions would age normally during their journey, but centuries or millennia would pass on Earth for every day they experience near the cosmic edge. The measurement of time itself becomes ambiguous near cosmic boundaries, where different observers disagree about the timing and sequence of events. What appears as a single moment near the cosmic edge might correspond to the entire future evolution of the universe from the perspective of observers in normal space-time. At the furthest reaches of space, information itself becomes trapped and distorted in ways that violate the fundamental principles of physics. The cosmic boundary creates an information paradox where knowledge about distant regions becomes permanently lost to observers in our local universe, challenging the quantum mechanical principle that information can never be truly destroyed. This cosmic information horizon transforms the edge of space into a realm where the very concept of knowledge reaches its ultimate limits. Quantum mechanics demands that information about the quantum state of every particle must be preserved throughout any physical process, even when matter falls into black holes or disappears beyond cosmic horizons. Yet the accelerating expansion of space carries information about distant galaxies beyond the reach of any possible observation, effectively erasing their quantum states from our accessible reality. The information paradox intensifies as we consider what happens to the quantum entanglement between particles separated by cosmic expansion. When two entangled particles are carried apart by expanding space until they cross the cosmic horizon, their quantum connection appears to be severed permanently. This breaks the non-local correlations that Einstein called spooky action at a distance, potentially violating the fundamental principles of quantum mechanics. Scientists have proposed that information lost beyond the cosmic horizon might be encoded in the cosmic microwave background radiation through holographic principles. Just as a hologram contains three-dimensional information on a two-dimensional surface, the cosmic boundary might preserve information about hidden regions in the pattern of temperature fluctuations we can still observe. The information paradox becomes even more mysterious when we consider the possibility of closed time-like curves near cosmic boundaries. If information can travel backward in time in these regions, it might be possible for knowledge about hidden cosmic regions to leak back into our observable universe through temporal loops. The cosmic edge becomes a realm where information transcends the normal flow of causality. Some theories suggest that the information lost beyond the cosmic horizon continues to exist in higher dimensional space, even though it becomes inaccessible to three-dimensional observers. The bulk space surrounding our universe membrane might serve as a cosmic library, containing complete information about all events that have ever occurred throughout the hidden universe. The quantum vacuum fluctuations near cosmic boundaries might encode information about regions beyond our horizon through subtle correlations in the pattern of virtual particle creation and annihilation. These quantum signatures could allow future technologies to reconstruct knowledge about the hidden universe by analyzing the statistical properties of empty space itself. Advanced civilizations in our observable universe might be able to circumvent the information paradox by sending quantum information toward the cosmic boundary at precisely calculated trajectories. By exploiting gravitational time dilation effects, they could potentially store information in regions where time passes very slowly, creating cosmic data archives that preserve knowledge for far longer than normal physical processes would allow. The information paradox also affects our understanding of consciousness and memory. If consciousness depends on information processing, then beings near the cosmic boundary might experience altered states of awareness as information about their own quantum states becomes ambiguous. The edge of space might represent the ultimate limit of self-knowledge and identity. Future theories of quantum gravity may resolve the information paradox by revealing that space and time themselves emerge from more fundamental information theoretic principles. In this view, the cosmic boundary might represent a transition between different levels of reality, where information transforms rather than disappears. Reality itself might be nothing more than a hologram projected from information encoded on the two-dimensional boundary of our universe, with all the depth and complexity we experience emerging from patterns written on an infinitely distant cosmic surface. The holographic principle suggests that every bit of information within our three-dimensional space can be completely described by data stored on the boundary of that space, making our entire universe equivalent to a cosmic movie projected from its edge. This mind-bending concept emerged from studies of black hole physics, where scientists discovered that all the information about matter falling into a black hole gets encoded on the black hole's two-dimensional event horizon surface. The same principle might apply to the entire universe, with all the galaxies, stars, planets, and even our own thoughts existing as projections from information patterns encoded on the cosmic boundary. The holographic principle transforms our understanding of what lies beyond the edge of space. Instead of additional regions filled with matter and energy, the hidden universe might consist purely of information encoded on a cosmic boundary surface. This boundary contains the complete blueprint for everything that appears to exist in three-dimensional space, including regions beyond our current observational horizon. The resolution of this cosmic hologram determines how much detail can exist in our reality. Just as a computer screen displays images using individual pixels, the holographic boundary might be pixelated at the Planck scale, with each pixel containing one bit of information about the projected universe. The total information content of our observable universe would then be limited by the number of Planck scale pixels on its boundary surface. The holographic encoding might explain why space appears three-dimensional to us, even though the fundamental information exists on a two-dimensional surface. Our brains and measuring instruments are themselves part of the hologram, programmed to interpret the projected information as three-dimensional experiences. The depth we perceive represents an emergent property arising from correlations between information patterns on the boundary. Time itself might be encoded holographically, with the apparent flow of causality emerging from the way information patterns evolve on the cosmic boundary surface. Past, present, and future could all exist simultaneously as different regions of the holographic encoding, with our subjective experience of temporal flow arising from the specific way consciousness processes the holographic information. The holographic principle suggests that communication with regions beyond our cosmic horizon might be possible by manipulating the information patterns on the boundary surface. Advanced civilizations might learn to write messages directly onto the cosmic hologram, creating changes in the projected reality that could be detected by observers in distant regions of the hidden universe. Quantum entanglement effects might represent correlations between different regions of the holographic boundary, allowing instant communication between widely separated parts of the projected universe. The non-local connections that Einstein found so troubling could emerge naturally from the holographic structure of reality, where distant regions of space correspond to nearby areas on the encoding surface. The holographic principle also raises profound questions about the nature of consciousness and identity. If our thoughts and memories are encoded as information patterns on the cosmic boundary, then consciousness might represent a specific type of information processing that occurs within the holographic projection. The boundary between self and environment might be an illusion created by the way holographic information is organized and processed. The ultimate paradox of the holographic principle is that it makes the concept of beyond the edge of space meaningless in the traditional sense, because space itself emerges from information encoded on its own boundary. Scattered throughout the hidden universe beyond our cosmic horizon, supermassive black holes create their own event horizons that serve as one-way boundaries in space-time itself. These cosmic monsters, some containing billions of times the mass of our Sun, warp space and time so severely that they create regions where the normal rules of physics break down completely. Each black hole event horizon marks a point of no return where matter, energy, and even information cross over into realms that remain forever hidden from external observers. The event horizon of a black hole represents the ultimate cosmic border, a spherical surface in space where the escape velocity equals the speed of light. Once anything crosses this boundary, it cannot send signals or return to the outside universe under any circumstances. From the perspective of distant observers, objects falling toward event horizons appear to slow down and freeze at the boundary, their images becoming increasingly redshifted until they fade from view. Supermassive black holes, in the centers of distant galaxies, create event horizons larger than the orbit of Neptune. These cosmic boundaries contain regions of space-time where millions of years pass in the outside universe for every second experienced by an infalling observer. The extreme time dilation near these horizons creates temporal islands where causality operates according to completely different rules than in normal space. The space immediately outside black hole event horizons experiences effects that challenge our understanding of reality. The ergosphere around rotating black holes creates regions where space-time itself is dragged along by the black hole's rotation, making it impossible for any object to remain stationary relative to distant stars. Matter in the ergosphere must move in the direction of the black hole's rotation, creating cosmic whirlpools in the fabric of space and time. Some theoretical models suggest that black hole event horizons might be permeable to certain types of exotic matter or energy. Quantum tunneling effects could allow information to leak out of black holes through virtual particle processes, while hypothetical tachyons traveling faster than light might be able to escape from regions inside the event horizon. These possibilities transform black hole boundaries from absolute barriers into selective filters. The information paradox reaches its most extreme form at black hole event horizons, where the quantum mechanical principle of information conservation appears to conflict directly with general relativity. Hawking radiation slowly evaporates black holes by creating particle pairs at the event horizon, but this radiation appears to carry no information about the matter that originally fell into the black hole. The resolution of this paradox might require revolutionary changes to our understanding of space, time, and information. Wormhole connections might link black hole event horizons to completely different regions of spacetime, creating cosmic tunnels that bypass the normal limitations of space travel. An astronaut falling through a black hole event horizon might emerge from a white hole in a distant part of the universe, having traveled through dimensions that exist outside our normal three-dimensional reality. The merger of supermassive black holes creates gravitational wave events so powerful they ripple through spacetime across cosmic distances. When two event horizons merge, they create new cosmic boundaries with properties that depend on the masses and spins of the original black holes. These merger events might briefly open windows into the interior regions of black holes before the new event horizon forms. Some models of quantum gravity suggest that black hole event horizons are not smooth surfaces, but rather turbulent regions where space and time fluctuate on quantum scales. These quantum horizons might allow limited forms of communication between the interior and exterior regions through quantum entanglement effects that transcend classical spacetime boundaries. The cosmic significance of black hole event horizons extends beyond individual objects to influence the evolution of entire galactic regions, creating islands of extreme physics scattered throughout the hidden universe. Deep within the hidden regions beyond our cosmic horizon, the fabric of spacetime might be riddled with cosmic tunnels that connect distant parts of the universe through shortcuts that bypass normal space entirely. These wormholes, if they exist, would create passages where travelers could journey billions of light years in moments, emerging in cosmic territories that would otherwise require longer than the age of the universe to reach. Each wormhole mouth would appear as a spherical region of distorted space, offering glimpses into alien skies and distant realms. The mathematics of general relativity allows for wormhole solutions where spacetime curves back on itself to create bridges between widely separated regions. These Einstein-Rosen bridges would appear as throats connecting two different areas of space, allowing matter and energy to pass between regions that might be separated by distances greater than our entire observable universe. The journey through a wormhole could take just minutes while spanning cosmic territories larger than galaxy superclusters. Stable wormholes would require exotic matter with negative energy density to prevent their throats from collapsing immediately after formation. This exotic matter would need to violate the normal energy conditions that govern ordinary matter, creating regions where gravity becomes repulsive instead of attractive. The cosmic boundaries of wormhole throats would be lined with this strange matter, creating portals where the normal laws of physics operate in reverse. Traversable wormholes connecting different epochs of cosmic history could allow time travel to regions of the universe that correspond to different stages of cosmic evolution. A traveler entering a wormhole in our current cosmic era might emerge during the epoch of galaxy formation. When the universe was younger and denser, these temporal wormholes would connect not just different regions of space, but different moments in cosmic time. The hidden universe beyond our horizon might contain natural wormhole networks created during cosmic inflation or phase transitions in the early universe. These primordial wormholes could link regions that were once causally connected but became separated by the expansion of space. The network might span the entire multiverse, creating a cosmic subway system connecting bubble universes and parallel realities. Quantum entanglement effects might stabilize certain types of wormholes through correlations between particles on opposite sides of the cosmic tunnel. These entangled wormholes would represent physical manifestations of quantum non-locality, where quantum mechanical connections create stable shortcuts through spacetime. Information sent through such wormholes might travel faster than light while preserving the fundamental principles of quantum mechanics. Microscopic wormholes in the quantum foam might constantly form and collapse on Planck-scale timescales, creating a dynamic network of temporary connections throughout spacetime. Advanced civilizations might learn to artificially expand these quantum wormholes into macroscopic tunnels, creating transportation networks that span cosmic distances instantaneously. The mouths of wormholes would create gravitational lensing effects that distort the appearance of objects viewed through them, making distant cosmic regions appear as if seen through curved mirrors. Travelers approaching a wormhole mouth would see space appear to bend and twist around the entrance, with the destination region visible as a circular window floating in space. Rotating wormholes might drag space-time around their mouths, creating ergosphere-like regions where the normal flow of time becomes entangled with the rotation of the cosmic tunnel. These effects could allow limited forms of time travel even without entering the wormhole itself, as objects in the ergosphere would experience complex temporal distortions. The existence of wormhole networks throughout the hidden universe could explain certain astronomical observations that appear to violate our understanding of cosmic evolution and structure formation. Beyond our cosmic horizon lie domains where matter exists in forms so alien they challenge every principle of chemistry and physics we have discovered. These exotic matter regions contain substances with negative mass that fall upward instead of down, materials that exist in multiple quantum states simultaneously, and particles that move backward through time while maintaining forward causality. The normal atoms that make up stars, planets, and living beings represent just one small island in an ocean of possible matter configurations. Negative mass matter would create gravitational fields that repel instead of attract, forming cosmic regions where objects accelerate away from massive bodies rather than falling toward them. In these anti-gravity zones, planets would orbit stars by being pushed outward by gravitational repulsion, while spacecraft would need to expend energy to move closer to massive objects. The interaction between positive and negative mass could create perpetual motion machines that violate our understanding of energy conservation. Strange matter regions might contain quarks combined in ways that do not occur naturally in our universe, forming quark soups with properties that transcend normal atomic structure. These strange matter clouds could convert ordinary matter into exotic forms through contact, creating expanding zones where familiar elements transform into alien substances. A single strange matter nugget the size of a marble could potentially convert entire planets into exotic matter configurations. Supersymmetric matter regions would be populated by sparticles, the hypothetical partners of normal particles predicted by supersymmetry theory. These cosmic domains might contain selectrons, squarks, and photons that interact through forces completely different from those governing ordinary matter. The chemistry and physics of supersymmetric regions would follow rules that make our periodic table look like a primitive approximation of material possibilities. Dark matter might exist in forms far more complex than the simple, weakly interacting particles usually proposed by theorists. Complex dark matter regions could contain dark atoms, dark molecules, and even dark life forms that exist in parallel to our ordinary matter reality. These dark matter civilizations might inhabit planets made of dark elements, orbit dark stars, and develop technologies based on physics we cannot directly observe. Exotic matter with imaginary mass could exist in quantum superposition states, where particles simultaneously possess multiple contradictory properties. These quantum matter regions would be populated by substances that exist as probability clouds rather than definite objects, with their properties determined only when observed or measured. The act of observation itself would cause exotic matter to collapse into specific configurations. Magnetic monopole matter might exist in cosmic domains where individual north and south magnetic poles occur separately rather than always appearing in pairs. These monopole regions would support forms of electromagnetism completely different from our experience, with magnetic currents and electric fields that operate according to alien principles. The technology possible with magnetic monopoles could transcend every limitation of conventional electronics. Tachyonic matter moving faster than light could populate regions where causality operates in reverse, with effects preceding their causes and information traveling backward through time. These tachyonic domains might serve as cosmic archives where the future influences the past, creating temporal loops that preserve information about events before they occur. Axion matter regions might be filled with hypothetical particles that interact primarily through their coupling to electromagnetic fields, creating cosmic domains where light behaves in completely unexpected ways. These axion clouds could bend and twist electromagnetic radiation without any visible source, creating optical illusions and gravitational lensing effects that appear to violate conservation of energy. The boundaries between exotic matter regions and normal matter zones could create cosmic laboratory conditions where different forms of physics meet and interact, potentially revealing new principles that govern the relationship between alternative matter configurations. In the deepest reaches of space beyond our horizon, there might be expanding bubbles of alternative reality, where the fundamental laws of physics are rewriting themselves at the speed of light. These vacuum decay bubbles represent cosmic catastrophes, where the quantum vacuum transitions from a false stable state to a true minimum energy configuration, unleashing forces that transform matter, energy, space, and time into completely new forms. Once started, these cosmic avalanches cannot be stopped or escaped. Our universe might currently exist in a false vacuum state, a condition that appears stable but actually represents only a temporary equilibrium in the quantum field that fills space. Like a ball balanced on a hilltop that appears motionless but could roll down at any moment, our vacuum state might be waiting for the right quantum fluctuation to trigger a catastrophic transition to a lower energy state. When vacuum decay begins at any point in space, it creates an expanding bubble where the interior region operates according to completely different physical laws than the exterior universe. The bubble wall advances at exactly the speed of light, giving no warning to civilizations in its path. From inside the bubble, the transition appears instantaneous. One moment, you exist in a universe with familiar physics. The next moment, the fundamental constants have changed, and matter might not be able to exist at all. The energy released during vacuum decay exceeds anything possible through nuclear reactions or matter-antimatter annihilation. The quantum field transition releases the energy difference between the false vacuum and true vacuum states, potentially creating temperatures and pressures that dwarf those found in the cores of the most massive stars. This energy release could vaporize galaxies and create new forms of matter that cannot exist in our current universe. Inside vacuum decay bubbles, the masses of particles like electrons and quarks might change dramatically, making familiar atoms impossible to maintain. The strength of fundamental forces could increase or decrease by enormous factors, creating regions where nuclear fusion occurs spontaneously or where electromagnetic interactions become negligible. The chemistry and physics that support life as we know it would cease to function. The cosmological constant might take on different values inside vacuum decay bubbles, leading to dramatically different expansion rates for space itself. Some bubbles might contain regions where space contracts rapidly, crushing all matter into cosmic singularities within moments. Others might expand so violently that atoms are torn apart by the stretching of spacetime itself. Multiple vacuum decay bubbles could interact when their expanding walls collide, creating complex interference patterns where different sets of physics compete for dominance. These collision zones might produce hybrid regions where the laws of nature fluctuate chaotically between different possible configurations, creating cosmic battle zones where reality itself becomes unstable. The hidden universe beyond our horizon might already contain numerous vacuum decay bubbles in various stages of expansion, creating a cosmic mosaic where different regions operate according to incompatible physical laws. Our observable universe might represent just one island of stable physics in an ocean of regions undergoing continuous reality transitions. Some theoretical models predict that vacuum decay could be triggered artificially by high-energy physics experiments that probe the fundamental structure of space-time. Advanced civilizations attempting to understand the deepest laws of nature might inadvertently trigger vacuum decay events that transform their entire cosmic neighborhood into regions with alternative physics. The ultimate fate of our universe might depend on whether vacuum decay events eventually reach our cosmic neighborhood, transforming our familiar reality into something completely alien to our experience and existence. The quantum field that fills every cubic inch of space throughout our universe might be balanced on the edge of a cosmic cliff, ready to tumble into a configuration that would instantly transform or destroy everything we know. If our vacuum state is indeed false, stable for now, but not representing the true minimum energy state, then the entire cosmos exists in a condition of terminal instability that could end at any moment through a quantum fluctuation smaller than an atomic nucleus. The collapse of a false vacuum would begin with the spontaneous formation of a tiny bubble of true vacuum somewhere in space. This nucleation event could happen anywhere at any time, triggered by quantum uncertainty effects that are impossible to predict or prevent. The probability of nucleation depends on the energy difference between our current vacuum state and the true ground state, but even if this probability is extremely small, it becomes inevitable given enough time and space. Once nucleated, the true vacuum bubble would expand at exactly the speed of light in all directions, creating an unstoppable wave of physical transformation that would eventually reach every galaxy in the universe. Nothing could outrun this cosmic catastrophe because information itself cannot travel faster than light. Civilizations on planets in the bubble's path would have no warning until the moment their reality changed forever. The wall of the expanding bubble would appear as a spherical surface where the fundamental constants of nature undergo violent transitions. As this wall passes through a region of space, the masses of elementary particles could change by factors of millions. The strengths of forces could increase or decrease dramatically, and the properties of space and time themselves might transform into something completely alien. Inside the true vacuum bubble, atoms as we know them might become impossible to maintain. If the electron mass increased by a factor of 10, atomic orbitals would shrink so dramatically that chemistry could not function. If the strong nuclear force weakened significantly, atomic nuclei would fly apart, leaving only isolated protons and neutrons. Complex molecules necessary for life would disintegrate immediately. The energy released by false vacuum collapse could exceed the binding energy of all matter in the universe. As the quantum field settles into its true minimum, the energy difference gets converted into radiation and particle production on scales that dwarf stellar explosions. The vacuum transition might release enough energy to heat space itself to temperatures where even protons and neutrons decompose into their constituent quarks. Some false vacuum collapse scenarios predict that space itself would undergo dimensional transitions, changing from our familiar three-dimensional geometry to configurations with different numbers of spatial dimensions. Matter designed to exist in three-dimensional space would cease to function in four-dimensional or two-dimensional regions, making survival through the transition impossible for any known form of life. The cosmological constant governing the expansion rate of space might change during false vacuum collapse, leading to scenarios where the universe immediately begins contracting toward a big crunch, or expanding so rapidly that space stretches faster than the speed of light. Either outcome would prevent the formation of stable structures larger than elementary particles. Certain models suggest that false vacuum collapse might create pocket universes with completely different physical laws embedded within the expanding true vacuum regions. These baby universes would inflate rapidly and separate from our spacetime, creating new cosmic domains that evolve according to alternative versions of physics. Advanced civilizations might be able to detect the early stages of false vacuum collapse through gravitational wave signatures or subtle changes in the properties of quantum fields, potentially providing brief warnings before the transformation reaches their location. At the furthest reaches of cosmic time and space, our universe approaches an ultimate boundary where energy becomes so diluted and entropy so maximized that no work can be performed and no new structures can form. This heat death represents the final equilibrium state where temperatures equalize throughout the cosmos, leaving a cold, dark expanse populated only by isolated black holes slowly evaporating through Hawking radiation. Beyond this temporal horizon lies either eternal stagnation or the birth of something completely new. The heat death scenario emerges from the relentless operation of the second law of thermodynamics, which demands that entropy always increases in isolated systems. As the universe expands and ages, energy spreads out and becomes increasingly dilute while entropy approaches its maximum possible value. Eventually, all temperature differences disappear, ending the energy flows that power stars, galaxies, and life itself. In the heat death universe, protons themselves might decay after lifetimes of 10 to the 34 years, dissolving the atoms that make up all matter into leptons and photons. This process would erase the chemical elements forged in stellar cores, reducing the entire periodic table to a thin soup of electrons, positrons, neutrinos, and photons. The complex structures that once formed planets, stars, and living beings would become physically impossible to maintain. Black holes would become the dominant objects in the heat death universe, containing most of the remaining mass energy, while slowly shrinking through Hawking radiation. The largest supermassive black holes would take 10 to the 100 years to evaporate completely, outlasting every other structure in the cosmos by unimaginable margins. These cosmic monsters would represent the final islands of organized matter in an otherwise empty universe. The quantum vacuum fluctuations might become the most energetic processes in the heat death universe, creating brief sparkles of virtual particles in an otherwise motionless cosmos. These quantum events would represent the only remaining source of change and complexity in a universe that has reached maximum entropy. Occasionally, large-scale quantum fluctuations might spontaneously create organized structures, but these would dissolve back into thermal equilibrium almost immediately. Some theoretical models suggest that quantum tunneling events could trigger new episodes of cosmic inflation, even in a heat-death universe, creating baby universes that escape the entropy maximum of their parent cosmos. These vacuum fluctuation-induced Big Bangs would represent cosmic resurrection events, where new realities emerge from the quantum foam of the dead universe. The heat-death boundary might not represent a true end, but rather a phase transition to a different mode of cosmic existence. In this view, maximum entropy states could spontaneously reorganize through quantum mechanical processes that operate on timescales far longer than the current age of the universe. The apparent death of the cosmos might mark the beginning of exotic new phases of reality. Closed, time-like curves near the heat-death boundary could create temporal loops where information and energy cycle endlessly without violating thermodynamic laws. These time loops might preserve pockets of organized complexity even after the universe reaches thermal equilibrium, creating temporal islands where entropy remains finite despite the global maximum entropy state. Advanced civilizations might be able to postpone or circumvent heat death by harvesting energy from black hole evaporation, vacuum fluctuations, or exotic processes that operate near the fundamental limits of physical law. The technology required for survival in a heat-death universe would need to function with energy sources billions of times weaker than anything currently available. The boundary between heat, death, and whatever lies beyond might represent the ultimate cosmic phase transition, where familiar concepts of space, time, matter, and energy transform into something completely transcendent. At the ultimate boundary of everything we can conceive, imagine, or mathematically describe, lies the most profound question in existence. What could possibly lie beyond the very concept of being itself? Here we reach the absolute limit of physical reality, mathematical possibility, and even logical thought. Beyond this final frontier might exist realms where the categories of existence and non-existence become meaningless, where the distinction between something and nothing dissolves into forms of being that transcend every framework we use to understand reality. The question of what lies beyond existence challenges every assumption about the nature of reality. If infinite universes, higher dimensions, and alternative physics still fall within the category of things that exist, then what could possibly transcend existence entirely? Perhaps there are forms of non-being that possess their own reality, states that are neither existent nor non-existent but represent entirely different categories of being that we lack the conceptual tools to comprehend. Some philosophical and physical theories suggest that existence itself might be just one possible state within a larger framework of meta-reality. Just as our universe might be one bubble in an infinite multiverse, existence itself might be one possibility within a vast space of alternatives that includes various forms of non-existence, quasi-existence, and modes of being that have no relationship to anything we could recognize as real. The mathematical concept of absolute nothingness, not just empty space, but the complete absence of properties, potential, or possibility, might itself be transcended by forms of meta-nothingness that exist beyond the absence of everything. These realms might represent negations of negation, creating forms of being that emerge from absolute void through processes that make the Big Bang appear as simple as a coin flip. Consciousness itself might represent a fundamental aspect of reality that transcends the normal categories of existence and non-existence. If awareness is truly fundamental rather than emergent, then consciousness might extend into realms beyond physical existence, creating forms of being that are neither material nor energy, but pure subjectivity, experiencing itself across dimensions of reality we cannot imagine. The ultimate boundary might be the point where mathematical description itself becomes impossible, where even the most abstract mathematical frameworks fail to capture the nature of what lies beyond. These trans-mathematical realms might operate according to principles that make our most advanced mathematical theories appear as limited as counting on fingers compared to quantum field theory. Some theories propose that existence cyclically emerges from and returns to absolute transcendence through cosmic cycles that dwarf the Big Bang and heat death. In this view, all of physical reality represents just one breath in an infinite cosmic respiration, where existence and absolute transcendence alternate across timescales that make eternity seem momentary. The very act of asking what lies beyond existence might create its own answer through the strange loop of consciousness contemplating its own ultimate nature. Perhaps the boundary of existence is defined by the edge of what conscious beings can conceive, making the ultimate frontier not a place but a limit of awareness itself. Language, mathematics, and even thought itself break down completely when attempting to describe what transcends existence. Any description necessarily brings the transcendent into existence through the act of description, creating paradoxes where the very attempt to understand the beyond existence automatically fails by making it part of existence. The deepest mystery remains whether the question of what lies beyond existence even makes sense, or whether it represents the ultimate cognitive illusion. A question that appears meaningful only because of the limitations of minds evolved to survive in three-dimensional space rather than to comprehend the absolute nature of reality itself. We have journeyed from the familiar edge of our observable universe to realms so alien they challenge the very meaning of existence itself. What began as a simple question about what lies beyond the cosmic horizon has revealed layer upon layer of mystery, each more profound than the last. From dark matter kingdoms and inflating multiverses to vacuum decay bubbles and the transcendence of existence itself, we have discovered that our reality represents just the tiniest fraction of what might be possible. The true wonder is not just that these hidden realms might exist, but that conscious beings like ourselves can even conceive of them. We are cosmic accident made of star stuff, yet we can imagine infinite dimensions, parallel universes, and forms of being that transcend existence itself. Our minds, evolved to find food and avoid predators on the African savanna, have somehow developed the capacity to contemplate the ultimate nature of reality. Perhaps the greatest discovery of our cosmic journey is that the universe is far stranger, far larger, and far more wonderful than we ever dared imagine. Every answer reveals new questions that stretch the boundaries of possibility even further. The edge of space is not a wall, but a doorway to infinite mystery. What lies beyond the edge of space? Everything and nothing. Something and its opposite. Realities we can imagine, and others that transcend imagination itself. The universe keeps its ultimate secrets hidden, not because they are forbidden to us, but because they are so magnificent they would transform us completely if we could truly understand them. The cosmic frontier calls to us still, inviting us to push beyond every boundary, question every assumption, and never stop wondering what impossible marvels await discovery in the infinite expanse of possibility. In the end, perhaps the journey itself is the destination, and our capacity to wonder about what lies beyond is the most cosmic thing about us. Subscribe to join us as we continue exploring the deepest mysteries of existence, and remember, in a universe this strange and wonderful, anything is possible.